Yep, checks out. Thank you.
Okay, so we were just going to talk about a little bit about assignment from 2.1. This was using a really basic technique, a type of substitution basically, or elimination maybe, to solve simple systems of two equations and two unknowns. And so it sounded like in general people were happy with how it went. When I asked people how it went, we only heard high numbered problems, right? Malia, I think we mentioned number 45. Was somebody else uncomfortable with number 45?
Yeah.
You were too? Let's talk about number 45, even if not everybody was all that uncomfortable with it. It says on number 45, which is on page 53, it says birds. The date of the first sighting of robins has been occurring earlier each year over the last 25 years at Rocky Mountain National Biological Laboratory. Scientists at this laboratory have developed two different linear equations that estimate the date of the first sightings of robins, where x is year and y is the estimated number of days into the year when the robin is expected. Compare the date of the first sighting in 2000 for each of the two equations. Hint, that was a leap year. Okay, they're way overthinking this here. So that first one, the first part of that, all they mean is plug in 2000 for year, which is x, right? And you're going to get a y, which is the date in that, the Julian date. Do you know that word Julian date? Julian date means counted from the beginning of the year. So like February 1st is the 32nd day of the year. And December 31st would be the 365th day of the year. Okay, so you just plug 2000 into the two different equations to come up with two different estimates of what was the first day the robins appeared in 2000. That wasn't so hard, right? Did you Malia, did you get that one to work? Yeah. Did you get that one to work? Okay, so that part wasn't really so hard. When I was looking at that, I was screwing it up because I kept thinking this was, you know, all of our textbooks have a tendency to take the 2000 off, and I thought we were supposed to plug in 0, and I was like, wait, how is this working? Oh, then I saw. Okay. Okay, so another, then it says, solve this equation to find the year in which the two estimates agree.
Well, that's when you just substitute the equations with each other, and then you just do some dividing, and then you have to round it out.
Okay, hold on. So we have two equations. Hold on. And you want them to agree. Hello, Luke. So if you have two equations, then you want them to agree. What does that mean? Hold on. 759 minus 0.338x is one of your equations. And the other one was y equals 0.0779x. What does it mean? What do we want to do here that it means? Maybe we want to find the date on which they agree.
Well, first you have to start rearranging some stuff so that you have y plus 0.338.
Yeah! One of the things that's confusing about this compared to other problems you have is it doesn't look like other problems you had, right? It doesn't have something x plus something y equals something. It's different. And so let's rearrange this into a format that looks a little better. I mean, I could have guessed just pulled this x over to this side, and in this case have 0.338x plus y equals 759. And on this one I could pull this x thing over to this side and have 0.779x plus y equals 1637. Okay, so first off, I agree with that. I think it could be very helpful to make this look like something. Something that is familiar to us. Alright, now what does it mean in the question though? Solve this set of equations for the year in which the two estimates agree. What does that mean?
It means you have to find, like, because x equals years, you have to find out a value that would equal the same as x in both equations.
You're trying to find a place where the same combination of year and date, same combination of x and y, work for both equations, right? In other words, you're trying to solve this one, right? These are two different graphs of lines where, like, one line looks like this, and one line looks like this, and where they have x, which is year, this way, and Y, which is the date the birds show up. And on each year, there's a slightly different value, 2 different guesses as to when the birds would show up. They agree at this place where they crossed. The 2 different estimates agree with each other on there. So I thought this problem was weirdly worded, and then it comes back to exactly what we've been doing all along. Right? It could have been tempted. As I see when I look at people's homeworks, my guess is people might have thought this was somehow a very different kind of problem. Like maybe they were trying to set one side equal to the other side.
That's what I originally tried to do, and then I looked at the problem and I checked the answers in the back of the book.
Yeah, anybody who got down that path would not have been, well, that would have been a reasonable thing to guess. Okay, it just wasn't right.
So you don't set them equal to each other? Wait,
No, it's 2 equations. I mean, basically we're looking for the place that is, here's one graph, here's the other graph. We want to find the place where this value of x and y works for both of them.
Okay.
So it's a weirdly worded question. It sounds like it's a different thing than it is. In the end, this problem really is the same thing as all the other ones. Now, getting this thing solved is no sense of fun. Oh wait, it's not that bad at all. If I multiply the bottom one by -1,
The top one would be easier than everything.
you want to modify the top one? Yeah, sure, what the hell. Let's make the top one by -1. I'll just put a little negative sign there. And add them together. This plus this will just be something. This plus this will be 0. This plus, you'll get some number of x equals something. It's actually not that bad. What did you get anyway?
Well, the original part was 1990.9, but that's not a year, so you round it up to 1991.
Okay, so they were in agreement in 1991. And what did you get for the date? Just out of curiosity, the Julian date.
That's not, it didn't ask for that.
Oh, okay. All right, but you could have plugged that in for x, and you could have gotten that works out to, let's just say, the 73rd day of the year.
Yeah.
Right, and then you could have counted that out, or you could have, I don't know, meteorology does a lot of things in Julian dates. I would have been perfectly happy with it. It's the 73rd day of the year. But the book, I think in the teacher's thing, actually did convert it into, which works out to March 3rd or something like that. I don't really care.
That's not what it said in the back.
Yeah, I don't particularly care. Yeah, whatever. All right. Hey, somebody had a different one they also wanted to talk about. 47. Basketball. Wilt Chamberlain holds the record for the highest number of points scored in a single NBA game. Jim Chamberlain scored 100 points for Philadelphia against the Knicks in 1962. This is an amazing feat considering he did it without a 3-point shot. I don't think they had 3-point shots in the NBA back then. I don't know. So, he made 64 baskets, 64 field goals, 2 points, and, wait a minute. He made a total of 64 baskets, including the field goals. All right, so what is the number he had to have made? Okay. All right. Sports questions. Damn it. I'm sure I look like a guy who knows a lot about sports. There was a little teacher, get to know your teachers survey kind of thing we had to fill out for the incoming freshmen. And there were questions about what sports do you like to play, what sports do you like to watch. I'm like, kids. I got nothing. All right, let's say X is the number of field goals, which is the right word, 2-point shots. And Y is the number of free throws, 1-point shots. Because that's what the problem is trying to solve for. How many of these should he get? We know he need a total of 64 shots, right? In other words, X plus Y is 64. That's what it actually says in the book, right? Yeah, okay, just double checking. Okay, and the amazing thing is it adds up to 100 points. So apparently, well, he made this many 2-point shots, so the total number of points he made is 100, and that is 2 times the number of field goals he made, plus the number of free throws he made. Right? broken this record? Anybody knows more about sports than I do? Has anybody broke, has LeBron or anybody broken this record?
Probably.
What sport is
I don't
this
know.
in?
I have no idea.
That sounds stupid.
Oh, God bless you, Malia. She asked what sport this is. This is basketball.
Oh, okay.
I know,
God bless you, Malia.
I know nothing about basketball.
I don't either. All right. Once we got it into this form, it's not going to be all that hard, right? I mean, here, let's make this negative x minus y is negative 64. And let's add these two equations together to get a new equation, which will be x equals 32. 36, thank you. All right, so we made 36 field goals, which means y is going to be, how many? 28? All right. So once you got it into this form, it wasn't that hard. When I was making the key for this one, thought this one was tricky to think through, especially considering it was a little clumsy how it was worded. Okay? But, yeah, once you had this one worked out, it wasn't that big of a deal. Are we happy? We're happy. We can talk more about this. I want to get into new material before we run out of battery like we did the other day. I got to get some battery. The rechargeable batteries last longer in here, but I can't find my charger. My house is torn up. You guys know about it. I told you about this. We're remodeling my house. I can't find the charger. I can't find our dishes right now because we're remodeling. The fact that I can't find a charger doesn't really surprise me. And these video cameras, they eat just ordinary store-bought battery like you wouldn't believe. So.
At least you're not coming to school half high on paint so.
Oh my gosh.
That's what happened to me. Was we started remodeling our house like 3 years ago and we painted and
Wow. It's no fun. Don't do it.
don't remodel.
Just move. All right. Today we're basically solving the same exact kind of problems. We're just going to be using a different technique. Now remember we talked about the other day, back in pre-calc or something like that, we had a whole chapter about techniques. We may have even had 2 chapters. We had elimination, substitution, Gauss-Jordan, echelon method, reduced row echelon form, Kramer's rule. There were so damn many of them. It was like 2 chapters of the book. We are only going to do 2 at this time, and this is the second one, and we happen to be doing Gauss-Jordan. Oh, Friedrich du Gauss. I don't know who Jordan was. Gauss-Jordan method. But it's for solving the same exact kind of problem. Gauss-Jordan is another strategy where we're going to be getting problems into a form like 3x plus y minus z equals 10 and 2x minus y plus 1z, I'll make it 11z equals 5, and y plus z equals 8. You're going to get them into you get a system of equations. There are linear equations. Linear meaning there's no crazy things in it like sines or squares or something like that, okay? Just coefficients and variables. And what makes it a system of equations here is that there's the same number of variables as you have equations. Like I think all the ones you did on the last assignment were 2 variables and 2 equations. Am I right about that, Lisa? I can't remember. Or did you? Somebody. I think there were, sometimes there are 3 variables, whatever. Gauss-Jordan is the method where we're going to start making this a little more like a game. Well, I mean, we're going to be using matrices. Where we're going to say, once you have it in this nifty format, something x plus something y plus something z equals something, we're going to make these coefficients that are in front of each of these variables, and we're just going to make a matrix of them. You might remember that there were all kinds of examples of doing this back in pre-calc. MJ, there's a point in the future in which you will remember having done this in pre-calc.
Okay.
But you just put them in there like into rows and columns of a matrix. And then we drew a line and we put these numbers. 10, 5, 8. There was a word for this kind of matrix. It was called an augmented matrix. They throw that word around a few times in the chapter here. But an augmented matrix means that it has this extra column in here. Notice the terminology here. There are rows and there are columns. Now, when you're doing anything with matrices, and we'll be doing a lot of things with matrices in this class, you can do matrix row operations. There are things we can do to change rows. And there's going to be a strategy as to what we're going to do to these rows. There's always a strategy as to what we're doing when we're doing a matrix. What we want to do is we want to find ways to change this matrix. We're going to find out after a series of steps, and we want to get it so that our matrix still has numbers here, here, and here, and still has numbers on the diagonal. I'm just going to use little squiggles here to mean like a number. But every place else is a 0. We are going to do operations to our matrix until we get it so that there's just numbers along the diagonal and numbers on the augmented side of it, on the other side of the line. But everything else is a 0. You might remember from pre-calculus last year, there's a difference in this book versus the pre-calculus book as to whether these guys here along the diagonal have to be 1 or not. Okay? One textbook says, Gauss-Jordan says, do it until you get those to be 1s. One book says Gauss-Jordan doesn't care. Okay? It turns out you're going to get the same answer either way. I don't care whether you take that one extra step to get it there. I just want to check something real quick as to what that was on my phone. Hold on. Just double checking. Hold on. Nope. Hold on. Sorry about that. This was the first day my youngest is being babysat by somebody before he goes off to kindergarten, and I mean I'm fully expecting the oh God, where are the kind of questions. You know what I'm saying? Like oh God, he got into a bottle of pills or something. Anyway, all right. So please don't get him into any bottles of pills or anything. Anyway, all right. So we can do things to these equations. And here's the deal. This is going to look familiar to you. The same things we were doing to equations before, where we added this one to this one, or we multiplied this one by some number, is exactly what we're doing to rows. And we do it just like we did in the process of elimination when we were talking about last time. We're doing it to get rid of numbers. Like for example, this 2 needs to go away. We need to do whatever the hell it takes to get that thing to go away and make it a 0. Alright, that one might be slightly hard. Let's start with something easier on this particular one. How about we know we got to get rid of this guy. He's got to become a 0. What could we do to get this one to go away? Well, we could take, just like we could if we were over here, we could add these 2 equations together. Should I even look at what my phone message is?
Yes.
You could add these 2 equations together here. This one plus this one to make this one go away. But it's going to take some practice to get this to all work. Alright? So, let's do one of the ones they've got. So you could be looking at it along the way here. Hold on. Which one shall we do? Let's do one that's simpler for one thing, not 3 rows and 3 columns. That's just too much to work through. Let's do a simpler one. How about example 1 on page 56? I probably should look what that chirp is. Again, house on fire, can't find the child. Nope, don't care about that. Alright. Alright, so the set of equations is there at the top of example 1, but we can write it real quick as that augmented matrix 3 minus 4, 5, 2, and then the augmented side is 119. Okay, and we want to get it into a form where the things on the diagonal, this guy and this guy, are still there, but these things become 0. Alright, Let's target, how about, let's get rid of this guy. Okay, a minus 4. If I took row 1 times a half to get the new row 1, we would have 3 halves, negative 2, 1 half. And the bottom row hasn't been changed. I don't know if that's exactly, maybe I should be doing it the same way the book did. Hold on.
The book is doing it really weird.
The book is doing it really weird?
Yeah.
Oh my god, did they go into like fraction land?
Yeah.
Yeah, I probably will too. It's probably a weird number. Let's try. Let's try to not look at the book as to how the book did it.
Yeah. Or you
All
can
right.
just multiply the bottom row by 2.
Or I could have multiplied the bottom row by 2. I like MJ's idea better because that will keep us away from fractions longer. Let's do that. So row 2 times 2 becomes the new row 2. By the way, I'm not sure there's any like official notation of how to do this, as long as you made a note to yourself what you did. Okay? Like you might see how they keep having these little notations here? I mean, whatever helps you know what you did. So in other words, we didn't change row 1, and we multiplied this row by 2. All right, that makes me happy-ish. All right, then what can we do with this one? Let's make row 1 plus row 2 becomes the new row 1. Because that's a fair thing to do. You can take one row and add it to another, and just put them down in the sum in there before. So this is now 13, 0, 39, 10, 4, 38. Okay. Alright, what do we also have to get rid of? Which number on there also must go away?
10.
That 10. Okay. 10 and 13 are not going to be easy to get rid of. I would say, let's just go for their least common multiple or whatever, which 5 times 13?
Was 13 times 5? No, that's not.
Yeah, that's not going to do it, is it? No, we're just going to multiply by 10 and the bottom one by 13. Oh, this will be fun.
The answers are full, not like whole numbers.
Oh, it will? Alright, we'll get there. Cool. I'm happy about that. Alright, so let me bring up my calculator.
They're actually the diagonals in that first matrix.
What?
In that first matrix, the answers are those two numbers.
Really? That's a coincidence. Alright, let's multiply the top row by 10, and let's multiply the bottom row by 13. Alright, so that top row becomes 130, 0, 390, and let's multiply that bottom number actually by about 100, negative 13. 4 times negative 13. Let me confirm it here. Negative 52. And 38 times negative 13 is negative 494. See what I did here? I made it so that because look what I'm going to be able to do. I will now be able to get rid of this guy pretty easily, right? Because we've got a 130 here and a negative 130 here. It will be pretty easy to say row 1 plus row 2 becomes the new row 2. So, whoops, let's switch this over here. So 130, 0, 390, 0, negative 52, negative 400. Oh, wait, I got a problem here. Row 2 plus that one. What's...
It's 104.
Is it 104? Okay, 104.
Oh, negative 104.
Negative 104. All right. I like the idea of making these numbers ones. How would I make these numbers 1? I could take the top row and divide by 130. Row 1 divided by 130 becomes the new row 1. And row 2 divided by negative 52 becomes the new row 2 is a perfectly fine thing. If you do it this way, your new matrix will have 1s, right? 130 divided by 130 is 1. 0 divided by 130 is 0. 390 divided by 130 is 3. Do that same thing for the bottom row. 0 divided by, who cares? Negative 52 divided by is 1. Negative 104 is 2. Why is this the happy way of doing this? What have I, by making the Gauss-Jordan method have 1s along the diagonal like that, what have I done nice?
X equals 3, y equals 2.
Now, we just pick the answer out. This is x, and this is y. And if you plug that back into our original equation, it'll work. Now, it would have worked here too if you said 130x equals 390 and negative 52y equals negative 104, but that can be error prone. You can make what mathematicians technically call a boo-boo. Okay? It is in general better to get it so that it's just this and with 1s along the diagonal, and then you have the x and the y. Now, for 2 equations with 2 unknowns, this is a bit messy. For 3 equations and 3 unknowns, it starts getting really messy. Now, because 7 of the 8 of us, or however many there are when everybody's here, did this to death, and MJ's really good at math, I'd rather not spend a bunch of time doing those ones with 3 rows and 3 columns, like example 2, it takes a while. Okay? I mean, this 2-row and 2-column thing took us quite a while here. But I do want you to kind of get some practice doing those because they can be kind of tricky. It can be hard to figure out the strategy of what to get rid of and when. I will show you though, if you look at example 2, notice their plan. Like a hunter, they had a target. What they want to do, if they have a 3-row and 3-column matrix, so they've got blah, 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 all these numbers here. More numbers, blah, 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 blah. If you just go willy-nilly and attack all over the place, just trying to make, a bunch of these guys need to be 0. But there's a plan. It works best to pick a column and fight with that column first. Okay? So like, do the necessary row operations to get this 0. Once you have this guy 0, getting this guy 0, well, do all operations on this until you get this guy 0. Now see how this column is kind of done? And other operations you do won't hurt things. Then, go after, say, this guy, but use these 2 rows to do it so that you're adding like this is just 0 plus 0. Right? See, here's the deal. If you start doing things like adding this row to this row, the problem is this thing won't be 0 again. Okay? You can get yourself into like traps here. Not so much traps, but like loops. You know what I'm saying? Where you keep doing operations and you keep screwing up the stuff you've already fixed and got down to 0. Okay? This plan of kind of isolating one column at a time can get you past that. Okay? But we'll get practice with that. But again, because I kind of want to send people on their way of working on that. Now, really, the main thing you need to be afraid of with these things is what about, remember there's possibilities, because it's a pain in the butt math textbook, there's going to be possibilities where there's no answer. Remember, like if we were talking about this in terms of like the graphs of these 2 equations, what we're finding is the intersection. What the solution is it's the intersection here. But what about if the 2 lines never cross? Or what if the 2 lines are right on top of each other and any set of points works? Oh, the book is going to be a pain in the butt every now and then, and find one of those. How will you know? The book has explanations there that you'll catch when you see it there. But you're going to hit situations where like you get 0, 0, 0, 1. Or something like that. Well, that means 0 times x plus 0 times y plus 0 times z equals 1. Does that work? Is there any number of x, y, z that will ever work 0 times x plus 0 times y plus 0 times z? No, you'd have 0 is equal to 1. That can't be right, right? That's how you'll know it's either any solution works or no solution works, okay? And the book will walk you through all that. Okay, I did not notice until during the faculty meeting today that I had not yet written an assignment for this one yet. So, well, things got a little crazy at the office yesterday. Okay. All right.
Someone brought the bottle of sparkling water and we just kind of lose control.
Oh, sparkling water? No, things got a little out of control yesterday. There were all kinds of technical problems going on that we were running around fixing. And all of a sudden it was time to go home. And you're like, oh, I don't know if I actually got my classes completed. I'm sure I did. I'm sure I took care of it. So, here's the deal. Okay. On page 65 and forward, let's see here. 1 through 4, all. I'm going to be honest, those are easy. Those are easy points. Let's do, just because they're good exercise, let's do 11 through, let's just say 14 all. These are good practice. They're just do one example. They're not saying solve the whole equation. They're saying just do that one operation. Okay? Like they're saying replace row 3 by -1 times row 1 plus 3 times row 3. They're just making sure, and then go look in the back of the book to make sure you know what you're doing for these operations. Okay? Alright, but then we actually start solving some systems of equations. Let's do 17 through 20 all. Now these are all examples. These are all 2 by 2 examples, 2 equations with 2 unknowns. And so those are going to be relatively simple. And let's do 27 and 29. These are all 3 by 3, but in the back of the book. See, there's always a lot of thinking, by the way, in case you didn't know, as to what problems you're doing, as to like what the strategy is. Why, like harder ones, I make sure they're in the back of the book so that you can check. Okay? All right, and then we usually do some of the application ones. Which ones do I like over here? I think. Let me look real quick here. Do you guys like problems that involve money? Do you like problems that involve science? Do you like problems that involve industry?
Money.
Money? Money?
I like industry better, but it's...
Industry? 45 and 47. 45 is a money problem, 47 is an industry problem. That sounds like a solution to me. All right, go ahead and get started working on those. You feel free to work in groups if you would like. Now, I have an assignment to pick up from you. Let me write down that this is what we did today, and then I'll grab the assignments from you in case you wanted to finish up those last little couple problems. Yeah, Lisa.
One assignment that was due last class, I emailed you it.
Yes, I saw it. I just haven't had a chance to attack that yet. Okay, great. All right, let me write this stuff down in the lesson plan for today, and then I'll attack more things. All right. 1, 2, 3, 4, 5, 6. We got 6 people here. Okay.